So we've introduced photogrammetry. Now we'll talk about how we actually do it. What are the steps we need to actually create these 3D models from our 2D photographs? And here's our basic steps. Firstly, we need to capture images. We then need to capture or extract features from those images and match them between successive images. Once we've done that, we can develop our structure from motion models and then do our dense point cloud mapping, where we create our 3D representation from a whole lot of individual points within our image, and then start filling them in and putting texture to them so we can create a nice 3D model. I already mentioned we need to take a series of overlapping images, and there's a number of different ways we can do this. If we're on the ground, we want to use a decent camera. So we can use these days our phone cameras because they've significantly improved in the image quality. We want to make sure that the detail's really there in our photographs. So high resolution digital SLR cameras are excellent for this sort of purpose. We've got different ways that we can capture those images. So they can be RGB images, they can be multispectral images, they can use thermal sensors. The most common though that we'd use is our RGB images, standard images that we can see the red, green and blue color channels of light. And with our lenses, we want to make sure that we don't have significant distortion within our lenses. So we want a lens preferably with that no distortion there. Otherwise, it's going to be very hard to match feature extracted points between images, because that feature extracted point may be on an area where we've got lens distortion. That will cause errors within our 3D model. We want to take a series of images, and typically what we do is, for example, if we're doing the close range photogrammetry, we'd take them as in a circle around the particular thing that we're trying to capture. If we're in a UAV doing the aerial imaging, we'd move along straight lines back and forth and take image, 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 and then move back image, 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 for example. If we're doing this close range, we'd often do a circle around it, and then we do a higher circle. So we've actually not just looking at something from the side, but also from above and having a view above those images as well. And we want a high degree of overlap between our images, something at least 50%, because where each of these images is going to capture the object from a different orientation, and we want to make sure there's enough features in there that we can have overlap between them and match those features between the different images. Because as we all know, things look different from different orientations as we look at them. Now, there might be some areas that have some key features that we want to make sure are captured really well, or maybe some features that have significant discontinuities in them, something sticking out, for example. We want to take a few extra pictures of those areas to ensure that we can 3D reconstruct those areas in particular well. Our next step is feature extraction, where we want to look, well, our software actually wants to look, this is done automatically for us. Our software will look through each of these images and extract key features. Often these key features are objects or edges of things or corners, things that we can see and hopefully see from different vantage points, different orientations between the different images. One of the common methods that's done with this is SIF, the Scale Invariant Feature Transform, which helps us identify features within images. And those features may vary somewhat in scale because some of our pictures may be taken closer or further away, or maybe some of them are rotated and things like that, and we can still match those between our different images. So once we've taken a whole bunch of pictures and we've identified a whole lot of features within those images, we want to match those features between our photos. Not just two photos, but all our photos that those features are actually present in. And our software generates a quality score, basically a match score of how close each of the image pairs and the features found within those image pairs are to each other. A high match score will indicate there's a high degree of confidence that it's correctly matched features between images, and a low score would indicate a low degree of confidence in terms of how well those images have been matched. Our next step is our structure from motion step, where we're creating our 3D point cloud from our 2D images. At this point, we can estimate our pose. Now, when I talk about pose, I'm talking about our orientation of our camera and our position of our camera. And with that, our depth, so how far our camera is away from the various objects that we're trying to compute. So we're estimating that for each of the image locations that we captured. And we might have, depending whether we're using something aerial or using something of a close range, we might have tens or dozens of images to hundreds or thousands of images, particularly for our aerial views. And then we create this 3D point cloud based on matches of key features found between each of those different images. When we're talking about features, we're not just looking at a couple of features within an image, but we're looking for a good number so we can have a good degree of commonality and matches between our different images. And so this will give us what we call a sparse point cloud. This sparse point cloud, we can see a 3D reconstruction of our object, but typically the texture's poor on these, and we've got lots of missing bits because there's lots of points that haven't been matched correctly between images. There's lots of reason why this is the case, but we'll come to those in some of our challenges around photogrammetry. What we then want to do is create our dense point cloud. And in our dense point cloud, our 3D render will look a whole lot better than what we had in our sparse point cloud. Here we fill in basically all those missing bits and create textures based on the pictures that we have taken. And this will give us images that look like almost a full resolution image that we can look at from multiple different directions. Now, in terms of the processing power, this is a hugely computationally expensive processing step. This is something that can take hours depending on the size of the image, the amount of data that we're working with.